Hello everyone. Today we will study maximum and minimum values. First of all, let me introduce what is maximum and what is minimum. Let f be a two variable functions. Let f be a two variable function. We say f has a local maximum at point A, B if f of AB is greater than or equal to f of sy for all points xy near AB. We say f has a local minimum at point AB if f of AB is less or equal to f of sy for all points sy near AB. Let D be a subset of the domain if point AB belongs to D and f of AB is greater than or equal to f of sy for all points sy. For all points sy in D, then we say f of AB is an absolute maximum then we say f of AB is the absolute maximum on D. If point AB belong to D and f of AB is less or equal to f of sy for all points xy belong to D, then we say f of AB is an absolute minimum on D. That's how we define maximum and minimum. Next, I would like to show you how to find local maximum and local minimum first. Let's first of all review how we find local maximum and minimum in your first semester calculus. Let's review this problem first. Let f of x equal to x plus 1 to the power 5 minus 5x minus 2. Find local maximum and minimums. Find local maximum and minimums. What should we do first? If I remember correctly, we first of all take derivative, then find critical points. If we take derivative, we have 5x plus 1 to the power 4 minus 5. Then we try to find critical points. We set the derivative equal to 0. Solve the equation for x. If I solve this equation for x, I have x plus 1 to the power 4 equal to 5 divided by 5 is 1. Taking the fourth root on both sides, x plus 1 equal to plus or minus 1. Then add 1 to both sides. 1 plus 1, so subtract 1 from both sides. 1 minus 1 is 0. Negative 1 minus 1 is negative 2. So those are critical numbers. So first step, find critical numbers. Then next, we use second derivative test. To find maximum minimum, we use second derivative test. You take the second derivative, we have 20x plus 1 raised to power 3. Then we substitute 0 and negative 2 into the second derivative. If I plug in 0, I have 20 times 0 plus 1 cube, which is 20, greater than 0. If I plug in negative 2, I have 20 times negative 2 plus 1 cube, which is negative 20, less than 0. If the second derivative is greater than 0, that means we have a local minimum at s equal to 0. If the second derivative is less than 0, that means we have a local maximum. If the second derivative is less than 0, that means we have a local maximum at s equal to negative 2. If I plug in 0, second derivative is greater than 0, we have a local minimum at s equal to 0. If I plug in negative 2, second derivative is less than 0, then we have a local maximum at s equal to 2. Then, in order to find local maximum, local minimum, we plug in the x value, find a y coordinate. So for local minimum, we have y equal to f of 0. We substitute 0 into the original function. We have 0 plus 1 to the power 5 minus 5 times 0 minus 2, which is 1 minus 0 minus 2, which is negative 1. So local minimum is negative 1. For local maximum, I substitute negative 2 and find a y coordinate. Substitute negative 2, I have negative 2 plus 1 to the power 5 minus 5 times negative 2 minus 2, which is negative 1 plus 10 minus 2, which is 7. So local minimum is negative 1. Local maximum is 7. So keep the general step in mind. In order to find local maximum, local minimum, we first of all find critical point. Step 1, find critical point. Find critical numbers first. Step 2, use second derivative test. Use the second derivative test and determine which point is maximum, which point is minimum. That's the general step for local maximum, local minimum. And for two variable function, the procedure is very, very similar. For two variable functions, the procedure is very, very similar. So we know that in order to find local maximum, local minimum, we must find critical points first. Next, let me introduce what's called critical point. Let f be a two variable function. A point A comma B is called a critical point if both partial derivatives f sub x of a b equal to 0 and f sub y of a b equal to 0, or one of the partial derivatives is undefined, does not exist. So point AB is called critical point if both partial derivatives are 0, or one of the partial derivatives does not exist. Let's look at some simple example first. For each of the following functions, find its critical points. For each of the following functions, find its critical point. First one, f of sy equal to 2x squared plus 4y cubed plus axy. How do we find critical point? So first of all, I take partial derivatives. First of all, I find the partial derivatives. F sub x, I treat y as a constant, take partial derivative with respect to x. I have 4x plus ay. Then for f sub y, I take partial derivative with respect to y. I treat s as constant. I have 12y squared plus ax. Then I set both of them equal to 0. Since they are polynomials, it won't be the case that the partial derivative does not exist. So I set both of them equal to 0. Solve for x and y. I can try to solve for x in the first equation. If I try to solve for x from the first equation, I have 4x equal to negative ay, then x equal to negative 2y. Then I can substitute x into the second equation. I have 12y squared plus a times negative 2y equal to 0. Then solve the equation for y. Factor, I can pull out 4y. If I pull out 4y, I have 3y minus 4. Then solve the equation for y. I have y equal to 0, y equal to 4 over 3. Then for each y, I can substitute here, find x. When y is 0, x is negative 2 times 0, x equal to 0. When y is 4 over 3, x is negative 2 times 4 over 3, which is negative 8 over 3. So the critical point here is 0, 0, and negative 8 over 3 negative 8 over 3 comma 4 over 3. So those are the critical points. Next example, f of sy equal to e raised to power of xy squared minus x. So same procedure. I first of all take partial derivative. F sub x is e raised to sy squared times y squared minus 1. For f sub y, I have e raised to sy squared times 2sy. Then set both of them equal to 0. Solve for x and y. The second equation looks easier, so let me solve the second equation first. For the second equation, we know that exponential function cannot be 0. That means 2sy must be 0. So 2sy must be 0. Since exponential function cannot be 0, then 2sy must be 0. If I set 2sy equal to 0, that means either x is 0 or y is 0. When x is 0, I substitute 0 into the first equation, solve for y. I have e to the power 0 times y squared minus 1 equal to 0. E to the power 0 is 1, so I get y squared minus 1 equal to 0, y equal to plus minus 1. If I have y equal to 0, I substitute 0 for y, then solve for x. If I substitute 0 for y into the first equation, I have e raised to power 0 times 0 minus 1 equal to 0. This is impossible. Negative 1 equal to 0, that's impossible. So there's no solution. When y equals 0, there's no solution in the first equation. That means y cannot be 0. So we have two critical points here. We have two critical points. Zero comma 1 and 0 comma negative 1. Next, let me introduce the second derivative test. Let f be a two-variable function. Suppose f sub x of a b equal to 0 and f sub y of a b equal to 0 and suppose f has continuous second order partial derivatives. And suppose f has continuous second order partial derivatives. Near AB. Let D be defined as the determinant of the matrix f sub xx, f sub sy, f sub yx, f sub yy. Then D can be rewritten as f sub xx times f sub yy minus f sub xy times f sub yx. Since f has continuous second order partial derivatives, then by Crofts theorem, f of sy. F sub sy is the same as f sub yx. So this part can be rewritten as f sub sy squared, since f has continuous second order partial derivatives by Crowd's theorem. Fsy and fyx they are the same. I can write it as f of f sub sy squared. Now, the second derivative test says the following. Part A. If determinant d is greater than 0 and f sub xx of ab is greater than 0, or we can say f sub yy of ab is greater than 0, then f of ab is a local minimum. Part B. If determinant d is greater than 0 and f sub xx of ab is less than 0, or f sub yy of ab is less than 0, then f of ab is a local maximum. Part C. If determinant d is less than 0, then period, f is neither. Then f of ab is neither maximum nor maximum. Neither maximum nor minimum. It's not a maximum or min. It's not a local maximum or local minimum. And in this case, it's called a saddle point. If a point is not a local maximum, not a local minimum, it's called a saddle point. The fourth case, if d equal to 0, then the second derivative test is inconclusive. Then the second derivative is inconclusive. We cannot say anything about maximum, minimum. It could be neither. It could be maximum, could be minimum, could be neither. Then the second derivative test is inconclusive. If d is 0, if the determinant of the matrix is 0, the second derivative test is inconclusive. F of AB could be maximum, minimum, could be saddle point. That's the second derivative test. Now let me say a few things about second derivative test. This matrix here has a name. It's called the Hessian Matrix. This matrix here has a name. It's called the Hessian Matrix. This matrix has a name. It's called Hessian Matrix. And D is the determinant of the Hessian Matrix. Second thing, in the first statement, if D is greater than 0, f sub xx is greater than 0, or f sub yy is greater than 0, then f of ab is a local minimum. Have you think of a question? Or if f sub xx is greater than 0, f sub yy is less than 0, then what should we do? Is it possible that f sub xx is greater than 0 and f sub yy is less than 0? Is it possible? Let's look at determinant here. Since determinant is greater than 0, that means f sub xx times f sub yy minus f sub sy squared must be greater than 0. That's the first case. So this equation, if I move f sub xy squared over, I have f sub fx, f sub yy greater than f sub sy squared. And we know a perfect square must be greater or equal to 0. Since f sub xx, f sub yy is greater or equal to 0, then they must be either both positive or both negative. So f sub xx and f sub yy must be either both positive or both negative. So if we know one of them is positive, the other one must be positive. If we know f sub xx is positive, then we know f sub yy is positive. And similarly, if we know f sub yy is positive, f sub xx is positive. And same thing, if f sub xx is less than 0, is negative, then f sub yy must also be negative. So we only need to test for one of them. If one of them is positive, the other one must be positive. If one of them is negative, the other one must be negative. So keep the second derivative test in mind. This is the second derivative test. We will use it to find local maximum and local minimum. Keep this in mind. We will use it to find local maximum and local minimum. Next, let's try to find some local maximum, local minimum using the second derivative test. Look at the following examples. For each of the following functions, find its local maximum or minimum. For each of the following functions, find its local maximum or minimum. Let's look at a simple example first. F of sy equal to s minus 1 times y plus 2. So we first of all try to find the critical points. Take partial derivative. F sub x is y plus 2. F sub y is x minus 1. We set each of the partial derivative equal to 0. I have y equal to negative 2, s equal to positive 1. So my critical point is negative 2, comma 1. That's my critical point. Next, try to find the Hessian matrix. F sub xx, I take partial derivative with respect to x, I get 0. F sub xy, I find partial derivative with respect to y, I get 1. F sub yx, I take partial derivative with respect to x, I get 1. For f sub xx, sorry, f sub yy. find partial derivative with respect to y. Here I get 0. So the determinant of the Hessian matrix is f sub xx times f of sub yy minus f sub sy times f sub yx. I get 0 minus 1, which is negative 1. So at point negative 2 comma 1, determinant of the Hessian matrix is less than 0. So by the second derivative test, if the determinant of the Hessian matrix is less than 0, then this point is a saddle point. This is not a local maximum, not a local minimum. It's a saddle point. So there is a saddle point at negative 2 comma 1. If there's a saddle point, and that's the only critical point, and we find out this is a saddle point, then there's no local maximum, no local minimum. Another example. The f of sy equal to x to the power 3 minus 3sy plus y to the power 3. So let's first of all find the critical point first. Take partial derivative with respect to x. I have 3x squared minus 3y. For f sub y, I take partial derivative with respect to y. I have negative 3x plus 3y squared. Then solve the equations for x and y. Set both of them equal to 0. Solve the equations for x and y. In the first equation, if I solve for y, I have 3x squared equal to 3y. So y equal to x squared equal to y. If I divide both sides by 3, x squared equal to y. Then I can substitute y into the second equation. I have negative 3x plus 3 times x squared equal to 0. I replace y with x squared. Then solve the equation for x. This is a single variable function. Solve the equation for x. I get 9x to the power 4, 3x to the power 4 equal to 0. Factor, I can pull out 3x. I have negative 1 plus x to the power 3. Solve the first equation, I get x equal to 0. Solve the second equation, I get x cubed equal to 1. X equal to 1. Once I know x, I can try to plug in to find y. When x is 0, y is x squared, which is also 0. When x is 1, y is x squared. If I plug in 1 squared, I get 1. So critical points are 0, 0 and 1, 1. Next, we try to find the Hessian matrix. F sub xx, I take partial derivative with respect to x. I have 6x. F sub xy, I take partial derivative with respect to y. I have negative 3. F sub yx, I take partial derivative with respect to x. I have negative 3. F sub yy, I take partial derivative with respect to y. I have negative 6. I have positive 6y. Take partial derivative here with respect to y. I have positive 6y. Next, I compute the determinant of the Hessian matrix. Determinant of the Hessian matrix f sub xx times f sub yy, I have 36xy minus negative 3 times negative 3 is positive 9. Now, at 0, 0, the determinant at 0, 0 is, I plug in 0 for x and y. I have negative 9, which is less than 0. If determinant is less than 0, that means there's a saddle point. There is a saddle point at 0, 0. Next, another critical point is 1, 1. I plug in 1, 1 into the determinant. At point 1, 1, determinant is, I plug in 1, 1. 36 times 1 times 1 is 36. 36 minus 9 is 27, which is greater than 0. Then I test for f sub sx at 1, 1. If determinant is 0, it's greater than 0, we either test for f sub sx or f sub yy. Here, let me test f sub sx. I have 6 times 1, which is 6, which is greater than 0. So, by second derivative test, if determinant is greater than 0, f sub sx is greater than 0, then this is a local minimum. So, there is a local minimum at 1.11. The local minimum is f of 1, 1. We plug in 1, 1 into an original function. To find the local minimum, we plug in 1, 1 into an original function. If I plug in 1, 1 into an original function, I have 1 minus 3 plus 1, which is negative 1. So the local minimum is negative 1. Next example, f of sy equal to s cubed plus y cubed minus 6x squared plus 9y squared plus 9x plus 24y plus 19. So first step, we try to find the partial derivative first. F sub x, I take partial derivative with respect to x. I have 3x squared minus 12x plus 9. For f sub y, I take partial derivative with respect to y. I have 3y squared plus 18y plus 24. Next, we try to find critical points. So I set both partial derivative equal to 0. Then try to find critical points. Solve one of the equation first. They are both single variable functions. So we can solve both of them individually. If I solve the first equation, I can pull out 3. Make x squared minus 4x plus 3. Set equal to 0. Solve for x. I get s equal to 1, s equal to 3. Solve the second equation. I can pull out 3, make y squared plus 6y plus 8. Then I can factor. I have y plus 2 times y plus 4 equal to 0. So y equal to negative 2, y equal to negative 4. If there are 2 solutions for x, 2 solutions for y, the critical points could be s equal to 1, y equal to negative 2, s equal to 1, y equal to negative 4, or s equal to 3, y equal to negative 2, s equal to 3, y equal to negative 4. If we solve s and y individually, we must write down all possible combinations of s and y. If we solve s and y individually, we must write down all possible combinations for x and y. Next, let's compute the Hessian matrix. F sub sx, I take a partial derivative with respect to x. I have 6x minus 12. F sub sy, take a partial derivative with respect to y. I get 0 here. F sub yx, I take a partial derivative with respect to x. I get 0. F sub yy, take a partial derivative with respect to y. I have 6y plus 18. Next, we compute the determinant of the Hessian matrix. This is called Hessian matrix. Next, we find the determinant for the Hessian matrix. We have 6x minus 12 times 6y plus 18 minus 0. 0 is nothing. So that's the determinant of the Hessian matrix. Next, we test each point individually for local maximum, local minimum, or saddle points. At point 1, negative 2, determinant is, I plug in 1 for x, I get negative 6. Plug in negative 2 for y, I get positive 6. Negative 6 times positive 6 is negative 36, which is less than 0. So by second derivative test, there is a saddle point at 1, negative 2. Next, at the point 1, negative 4, determinant of 1, negative 4 is, I plug in 1 for x, plug in negative 4 for y. If I plug in 1 for x, I get negative 6. If I plug in negative 4 for y, I also get negative 6. Negative 6 times negative 6 is positive 36, which is greater than 0. When determinant is greater than 0, we test for f sub yy, f sub xx, or f sub yy. For f sub x, if I plug in 1, negative 4, I have 6 minus 12, which is negative 6, which is less than 0. So that means a local maximum. So there is a local maximum at the point 1, negative 4. The local to find out the local maximum, we plug in the point 1, negative 4 into the original function. Using my calculator, I get 7. So that's the local maximum is 7. Next point, at 3, negative 2. The determinant is 3, negative 2. I plug in 3 for x, plug in negative 2 for y. I have 6, 6 times 6, which is 36. Since determinant of the Hessian is greater than 0, I test for f sub xx or f sub yy. F sub xx is 3, negative 2. I plug in 3 for x. 3 times 6 is 18. 18 minus 12 is 6. That's greater than 0. So by second derivative test, there is a local minimum. There's a local minimum at the point 3, negative 2. And to find the local minimum, I plug in 3, negative 2 into the original function. Use my calculator, I get -1. And the last point, at point 3, -4. At point 3, -4. I plug in 3, -4 into the determinant. I plug in 3, -4 into the determinant. I have +6 times -6, which is -36. That is less than 0. So by second derivative test, there's a local, there's a settle point. There's a settle point at point 3, 4. Next, I will show you how to find absolute maximum and absolute minimum. First of all, let me introduce extreme value theorem. Extreme value theorem tells you under what condition there is an absolute maximum and absolute minimum. Let f be a two-variable function. Suppose f is continuous on a closed and bounded in a closed and bounded set D, where D is a subset of the domain. Then f has an absolute maximum at some point A, B belongs to D, and an absolute minimum at some points C, D in D. So if f is a two-variable function, suppose f is continuous on a closed and bounded set D, where D is a subset of the domain, then f has an absolute maximum at some point A, B in D, and an absolute minimum at some point C, D in D. First of all, what does the word closed and bounded means? What does the word closed and bounded means? What does a closed set means? Consider a set in R2. Consider a set in R2. XY plane is called R2. Consider a set in R2. If all boundary points are included in a set, then this is called a closed set. If all boundary points are included, this is called a closed set. If all boundary points are included. if some part of the boundary is not included. If some part of the boundary is not included, then this is not an open set. Not a closed set, sorry. This is not a closed set. If some part of the boundary is not included, this is not a closed set. Now what does the word bounded means? What does the word bounded means? If a set can be enclosed in a circle, if a set can be enclosed in a circle, then this is a bounded set. If a set can be enclosed by a circle, then this is called a bounded set. If a set cannot be enclosed in a circle, then it's not a bounded set. For example, consider the set here. Consider this set. Consider this set here. That's the set of points x between y between negative 1 and 1. That's the set of points x, y between negative 1 and 1. This is the set of x, y in R2. This is a set of s, y in R2 such that y is between negative 1 and 1. This is a set in R2, but this is not bounded. No matter how big the circle is, we are not able to enclose the entire set. This is unbounded set. This is an unbounded set. So if a set is closed, all boundary points must be included. If a set is bounded, it could be enclosed in a circle. It could be enclosed in a circle. So the extreme value theorem tells you in a closed and bounded set, if f is continuous in a closed and bounded set, then there is an absolute maximum and an absolute minimum. Next, I'll show you how to find absolute maximum and absolute minimum. First of all, let's review a single variable function first. Let's review a single variable example first. Let's review a single variable example first. Let f of x equal to 5 plus 54x minus 2x cubed. Find its absolute maximum and absolute minimum on the interval from 0 to 4. Find its absolute maximum and absolute minimum on the interval from 0 to 4. Is this set closed and bounded? Is this set closed and bounded? Interval from 0 to 4. First of all, this is a closed interval. So the boundary points are included. It's closed. This is a closed interval. The boundary points are included. So this is a closed set. And is this bounded? I can enclose this line by a circle. So this is closed and bounded. It is bounded. I can enclose these pieces of line by a circle. So this is closed and bounded. So by extreme value theorem, there is an absolute maximum, absolute minimum in the set. So first step, we take derivative, find critical points. First step, take derivative, find critical points. I have 54 minus 6x squared set equal to 0. I have 6x squared equal to 54. S squared equal to 9. So critical point is s equal to positive 3, s equal to negative 3. Negative 3 is not on the interval 0, 4. So this value is rejected. We only consider critical point on the interval. Next, we try to test for absolute maximum and absolute minimum. We test the boundary point and the critical point. To test for absolute maximum, absolute minimum, we test for the critical point and the boundary point. For this interval from 0 to 4, the boundary point is 0 and 4. Critical point is 3. Boundary point is 0 and 4. So we test for boundary point, test for critical point. If I plug in 0 to the function, I get 5. If I plug in 3, I get 113. If I plug in 4 to the function, I get 93. So the largest is absolute maximum. (113) is an absolute maximum. The smallest is absolute minimum. Absolute minimum is 5. So keep it in mind that absolute maximum or absolute minimum the absolute maximum or absolute minimum always located at the critical point or the boundary of the set. Of the set D. This is set D. We're finding maximum minimum of the set D. So absolute maximum, absolute minimum always located at the critical point or the boundary of set D. Next, let's look at some examples of two variable functions. For each of the following functions f, find its absolute maximum and minimum value on the given set D. On the given set D. First example, let f of xy be x squared plus xy, and let D be the set. Let D be the set of sy in R2 such that let D be the set of xy in R2 such that absolute value of x is less or equal to 2 and absolute value of y is less or equal to 1. Now, let's find the absolute maximum and absolute minimum. First of all, we know that absolute maximum, absolute minimum locate at the critical point and the boundaries. Let's draw set D first. In set D, absolute value of x is less or equal to 2. That means x is between -2 and +2. Since absolute value of x is less than 2, less or equal to 2, that means x is between -2 and +2. And also, since absolute value of y is less than 1, less or equal to 1, that means y by itself must be between -1 and 1. So if we draw the boundary, it looks like a rectangle. S between -2 and 2, y between -1 and 1. That's a rectangle. This is set D. Absolute maximum, absolute minimum may be on the critical point inside set D, or it may be on the boundary of D. So let's first of all find the critical point inside the set first. To find the critical point, we find a partial derivative. F sub x, we take partial derivative with respect to x. I have 2x plus y. For f sub y, I take partial derivative with respect to y. I get y. Then set each partial derivative equal to 0. Sorry, f sub y is x. If I take partial derivative with respect to y, I get x here. Then I set each partial derivative equal to 0. Solve the equations for x and y. Second equation already tells you s equals 0. So I plug in 0 into the first equation. I solve for y. Y is also 0. So the critical point is 0, 0. And we know 0, 0 belong to D. This 0, 0 belong to D. That's the critical point inside the set. Next, we try to find the critical point on the boundary. There are 4 boundaries. We try to find critical point on the boundary. This boundary here is y equal to 1. This boundary is s equal to 2. This boundary is y equal to -1. This boundary is x equal to -2. There are 4 boundaries. So let's look at the first boundary. On the boundary y equal to 1, x is between -2 and 2. On the boundary y equal to 1, on this boundary x is between -2 and 2. F of sy, if I plug in 1 for y, it can be written as f of s comma 1. If I plug in 1 for y, this function can be rewritten as f of s comma 1. So for f of s comma 1, I plug in 1 for y. I have x squared plus x. This is a single variable function. Let's call this function g1. This is a single variable function. Let's call this function g sub 1. If I take derivative, next we try to find critical point on this boundary. So I take derivative. This is a single variable function. If I take derivative, I have 2x plus 1. Set equal to 0. S equal to -1/2. -1/2 is between -2 and 2, so it counts. So when s is -1/2, y is 1. So critical point here is -1/2, 1. And the boundary of this boundary, is these 2 points. Keep it in mind. The boundary of this boundary, the boundary of this boundary y equal to 1 is these 2 points. We also need to keep these 2 points. There may be maximum, minimum, and these 2 points. This 2 point is the boundary of the boundary. So that's a critical point. That's the boundary of the boundary. We may have absolute maximum, absolute minimum here at these 2 points. Next, on the boundary y equal to -1. On the boundary y equal to -1, we have x is between -2 and 2. On this boundary, x is also between -2 and 2. If I plug in -1 for y, f of sy can be rewritten as f of x comma -1. I substitute -1 for x. I substitute -1 for y. I have x squared minus x. This is a single variable function. The variable is x. Let me call this function g2. g2 of x is x squared minus x. Next, I try to find critical point on this boundary. In order to find critical point, I take the derivative. g2 prime of x is 2x minus 1. Set equal to 0. I have x equal to a half. Half is between -half and 2. So the critical point on this boundary is half comma -1. S is half, y is -1. And also, the boundary of this line is these 2 points. We may have absolute maximum, absolute minimum on these 2 points, on the boundary of the boundary. So we also need to test these 2 points later. Next boundary. Next boundary is s equal to 2, this line. On the boundary, s equal to 2. On the boundary s equal to 2, y is between -1 and 1. So f of sy can be rewritten as, if I substitute 2 for x, it can be rewritten as 4 plus 2y. It can be rewritten as 4 plus 2y. This is a single variable function. Variable is y. Let's call this function g3. Variable is y. If I take derivative, I get 2. 2 can never be 0. So there's no critical point. There's no critical point on this boundary. There's no critical point on this boundary. But there may be maximum, minimum, and a boundary of the boundary. The endpoint of this boundary is -1 and 1. Keep these 2 points. We need to test it later. So there are no critical points on this boundary, but there are 2 endpoints here. We need to test these 2 endpoints later. On the boundary, s equal to -2 on this boundary here. Y is between -1 and 1. F of sy can be rewritten as f of -2 comma y. We substitute -2 for x. I have 4 minus 2y. This is a single variable function. The variable is y. Let me call this function g4. Variable is y. If I take derivative, I get -2. -2 can never be 0. So there are no critical points on this boundary. There are no critical points on this boundary. But maximum, minimum may locate at the endpoint of this line. Maximum, minimum may locate at the endpoint of the line. Maybe at these 2 points. So let's test it later. Now we have all critical points. Next, let's test for absolute maximum, absolute minimum. First of all, let's test for critical points. We have 0, 0. Critical point on the boundary is half comma 1, negative half comma 1, and half comma negative 1. And also, critical point may be on the boundary, maybe on the endpoint of the boundary. Critical point may be on the endpoint of the boundary. For y equal to 1, the endpoint is negative 2 comma 2. For y equal to negative 1, the endpoint is negative 2 comma 2. For s equal to 2, the endpoint is y equal to 1, endpoint is y equal to 1, negative 1. For s equal to negative 2, endpoint is y equal to negative 1, positive 1. So for critical point, we also need to, for absolute maximum, absolute minimum, we also need to test these four corners. So the four corners here is 1 comma 2, 2 comma 1. Two comma negative 1, negative 2 comma 1, negative 2 comma negative 1. These four corners, they are the endpoint of each boundary. They are the endpoint of each boundary. We also need to test for these 4 points, for absolute maximum, absolute minimum. So test critical point inside set D, test critical point on the boundary of D, and test critical point at the endpoint of the boundary. So that's the critical point. In D, inside, that's the interior critical point. Let's call it interior critical point. These 2 points, they are critical point on the boundary. They are critical point on the boundary of D. And these 4 points, they are critical point, they are endpoints of each boundary. Which is also called the corners. They are endpoints of each boundary, which is also called the corners. Next, let's plug in each point into the original function. Plug in here. If I plug in 0, 0, I get 0. If I plug in negative half comma 1, I get negative 1 over 4. If I plug in half comma 1, I get 3, 4. If I plug in 2 comma 1, I get 6. If I plug in 2 comma negative 1, I get 2. If I plug in negative 2 comma 1, I also get 2. If I plug in negative 2 comma negative 1, I get 6. So the largest is absolute maximum, which is 6. The smallest is absolute minimum, which is negative 1 over 4. Next example. F of xy is 3x squared plus 2y squared minus 4y. And D is the region. D is the region between curves y equal to x squared and y equal to 4. Since we are looking for absolute maximum, absolute minimum in set D, let's first of all draw region D, see how it looks like first. Let's first of all draw region D, see how it looks like. y equal to x squared is a parabola open upward. Y equal to 4 is a horizontal line going through 4 in the y-axis. So that's the region D. That's the region D. Now next, let's find the corner here first. Let's find the intersection here. What's the intersection here? When y equal to 4, x is positive 2 and negative 2. So this two corner here is 2, 4 and negative 2, 4. Now next, let's find the critical points. Absolute maximum, absolute minimum may be in the critical point or on the boundaries. So let's first of all find the critical point. F sub x, if I find partial derivative with respect to x, I have 6x. For f sub y, if I find partial derivative with respect to y, I have 4y minus 4. Then set each of them equal to 0. Solve for x and y. If I solve for the first equation, s equal to 0. If I solve for the second equation, y equal to 1. So critical point is 0, 1. 0, 1 somewhere here. It belongs to step D. Next, let's try to find critical point on the boundary. In this region D, there are two boundaries. First boundary is the parabola y equal to x squared. Second boundary is the horizontal line y equal to 4. There are two boundaries. Let's test the first boundary, y equal to 4. On the boundary y equal to 4. On the boundary y equal to 4, x is between negative 2 and 2. On this boundary here, x is between negative 2 and 2. So this function, if I plug in 4 for y, I have x, 4. I plug in 4 for y, I have 3x squared. If I plug in 4 for y, 4 squared is 16. 16 times 2 is 32. If I plug in 4 for y, I get 4 times 4 is 16. So, and this is a single variable function. Variable is x. Let's call this function g sub 1 of x. Let's call this function g1 of x. 32 minus 16 is 16. This is a single variable function. In order to find critical point, I take derivative. g1 prime of x is 6x. If I set equal to 0, I have s equal to 0. If I set equal to 0, I have s equal to 0. When s equal to 0, y is 4. So the critical point is 0, 4. And this 0 is between negative 2 and 2. So this 0 is valid. This 0 is between negative 2 and 2. This 0 is valid. So that's a critical point. And keep in mind that absolute maximum, absolute minimum may locate at the endpoint of the boundary. The endpoint of the boundary is these 2 points. The endpoint of this boundary is the point negative 2, 4 and 2, 4. Absolute maximum, absolute minimum may also locate at the endpoint of each boundary. So this 2 point is an endpoint of the boundary. We may have absolute maximum, absolute minimum at these 2 points. Another boundary on the boundary y equal to x squared. On this boundary y equal to x squared, x is also between negative 2 and 2 on this boundary. y equal to x squared. It's not an entire parabola. Only this piece. So for this piece, x is between -2 and 2. On the boundary y equal to x squared, x is between -2 and 2. If I plug in x squared for y, I have f of x squared. I plug in x squared for each y. I have 3x squared plus 2 times x squared minus 4 times x squared. I plug in x squared for each y. Plug in x squared for each y. Then simplify. This is a single variable function. Variable is x. Let me call this function g2 of x. If I simplify the function, I have 2x to the power 4 minus x squared. Then I take derivative. For g2 prime of x, if I take derivative, I have ax to the power 3 minus 2x. Set equal to 0. Solve the equation for x. I have 2x times 4x squared minus 1. Set equal to 0. 2x times 2x plus 1, 2x minus 1. Solve the equation for x. S equal to 0, s equal to -half, s equal to a half. 0 is between -2 and 2, that's fine. 0, x equal to -half. -half is between -2 and 2, so that's valid. Half is also between -2 and 2, so that's also valid. Then for each x, we need to find the corresponding y. Since we are looking for critical point on this boundary, y coordinate, from the y coordinate, I plug in x into the boundary here. And if I substitute 0 for x, y is 0. If I substitute -half for x, y is a quarter. If I substitute half for y is also a quarter. So the critical point on this boundary is 0, 0, -half, 1 over 4, positive half, 1 over 4. So there are three critical points on this boundary. And also, we need to include the endpoint of the boundary. The endpoint of the boundary is these 2 points. The endpoint of the boundary is these 2 points. Next, we try to test for absolute maximum and absolute minimum. When we test for absolute maximum, absolute minimum, we need to include critical points on the boundary, and the endpoint of the boundaries. So the interior critical point is 0, 1. Interior critical point is 0, 1. Critical points on the boundary. Critical points on the boundary is 0, 4. 0, 0. -half, 1 over 4. Positive half, 1 over 4. So these 4 points, they are critical points on the boundary. Next, we need to test the endpoint of critical point, the endpoint of the boundaries. The endpoint of the boundary is -2, 4. Endpoint of the boundary is -2, 4 and positive 2, 4. So 0, 1 is the interior critical point. 0, 4, 0, 0. These 4 points, they are critical points on the boundary. These 2 points, they are endpoint of the boundaries. These 2 points, they are endpoints of the boundaries. 0, 1 is the interior critical point. These 4 points is a critical point, they are the critical point on the boundary. And these 2 points, they are the endpoint of the boundaries. Now let's test the values. Plugging each of the point into an original function. Then find the maximum and minimum. Here I use my calculator. I get -2 for the first point, 16, 0, -1/a, -1/a, 64, 64. So the largest is absolute maximum. I have 64 is my absolute maximum. The smallest is my absolute minimum. My absolute minimum is -2. Next, f of sy is x squared minus 4sy plus 5. And D is the region. D is the set of xy in R2 such that S is between 0 and 4 and y is between 0 and square root of x. Since we are looking for absolute maximum, absolute minimum on region D, so let's first of all draw region D first. Since y depends on x, let's draw y first. Y equal to 0 is an x-axis. Y equal to square root of x looks like this. That's y equal to square root of x. X equal to 0 is here. X equal to 4 is a vertical line that goes through 4 in the x-axis. That's region D. The intersection between 2 points is here. For this point, x equal to 4. If I plug in 4 for x, y is 2. So this point is 4, 2. If I plug in 4 for x, y must be 2. So this point is 4, 2. That's region D. Next, let's first of all find critical points. F sub x is 2x minus 4y. F sub y is negative 4x. Set each of them equal to 0. If I solve the second equation, x is 0. If I plug in 0 into the first equation and solve for y, I have y equal to 0. So critical point is 0, 0. This 0, 0 belongs to D. This 0, 0 is here, that belongs to D. Next, let's try to find critical point on the boundary. This boundary here is y equal to radical x. This boundary is y equal to 0. And this boundary is s equal to 4. Let's find the critical point on each boundaries. On the boundary, y equal to 0. On the boundary y equal to 0, s is between 0 and 4. If I substitute 0 for y, I have f(x, 0) equal to x squared plus 5. This is a single variable function. Let me call this function f sub 1. Variable is x. Then I take derivative. In order to find critical point, I take derivative. I get 2x. If I set equal to 0, I have s equal to 0. When s is 0, 0 is between 0 and 4, so that's a critical point. When s is 0, y is also 0, so 0, 0 is a critical point. That's a critical point on this boundary. And also, for absolute maximum, absolute minimum, we also need to test the endpoint later. So these 2 points, the endpoints of this boundary. Next boundary, s equal to 4. on the boundary x equal to 4, y is between 0 and 2. On this boundary x equal to 4, y is between 0 and 2. If I substitute 4 for x, I have f 4 comma y. 4 squared is 16. 4 times 4 is also 16 plus 5. This is a single variable function. Let's call this function f sub 2. Variable is y. Let's call this function f sub 2. Variable is y. It can be rewritten as 21 minus 16y. Then I can take derivative. F sub 2 prime of y. Let's call this function g. To avoid confusion, let's call this function g. G sub 1 prime. Let's call this function g sub 2 prime. If I take derivative, I have negative 16. Negative 16 cannot be 0, so there are no critical points. There are no critical points on this boundary, but absolute maximum, absolute minimum may be on the boundaries, maybe on the endpoint of its boundary. So keep these two endpoints in mind. We may test it later. Next boundary. Next boundary is y equal to square root of x. On this boundary, x is between 0 and 4. So if I plug in square root of x for y, I have f of x comma square root of x. I plug in square root of x for each y. I have x squared minus 4x square root of x plus 5. This is a single variable function. Let's call this function g3. Variable is x. It can be rewritten as x squared minus 4x to the power of 3 over 2 plus 5. In order to find critical point, I take derivative. I have 2x minus 6x raised to a half. Set equal to 0. Solve the equation for x. Set equal to 0. Solve the equation for x. I can factor 2x to a half out. And what's left is x to a half minus 3 equal to 0. Then I have s equal to 0, square root of x equal to 3, s equal to 9. S equal to 0 is in the boundary. It's here. It's in the boundary. S equal to 0 is here. S equal to 9 is not on the boundary, so this point is rejected. It's rejected. This point will be rejected. So the critical point is x equals 0. When s is 0, y equals to square root of 0. Y is also 0. So critical point is 0, 0. Critical point is 0, 0. And the endpoint of the boundary is these 2 points. The endpoint of the boundary is these 2 points. There may be absolute maximum, absolute minimum, and the boundary, and the endpoint of the boundary. Now we know all critical points. Next, let's test for absolute maximum, absolute minimum. Let's draw a table. S comma y, f of sy. Interior critical point is 0, 0. This point is not interior, it's on the boundary. This point is not interior. This point is on the boundary. 0, 0. Critical point on the boundary. Critical point on the boundary is also 0, 0 and 0, 0. They are the same point, so only write it once. Next, we need to write down the critical point and the endpoint of each boundary. And the endpoint of the first boundary is these 2 points. The endpoint of this boundary is these 2 points. The endpoint of this boundary is these 2 points. So the endpoint of the boundary is 0, 0, 4, 0, and 4, 2. So the endpoint of the boundary is 0, 0, 4, 0, and 4, 2. So we plug in each point to an original function. Plug in each point to an original function and find out absolute maximum and absolute minimum. If I plug in 0, 0, I get 0, I get 5. If I plug in 4, 0, I get 16 plus 5, that's 21. If I plug in 4, 2, I get 16 minus 32 plus 5, which is negative 11. So the largest is absolute maximum. The smallest is absolute minimum. Next example, f of sy equal to 2 plus 2x plus 2y minus x squared minus y squared, and D is the region inside the triangle. With vertices zero, 0, 9, 0, and 0, 9. So since we are looking for absolute maximum, absolute minimum on region D, let's draw region D first. Region D is a region inside. D is a region inside the triangle with vertices 0, 0, 9, 0, 0, 9. Next region D. And the boundaries, this boundary is y equal to 0 on the x-axis, this boundary is y equal to 0. On the y-axis, this boundary is x equal to 0. How about this boundary? How about this boundary? This boundary is a straight line. This boundary is a straight line passing through 9 on the x-axis, 9 on the y-axis. So for straight line, we can use the form y equal to ms plus b. That's the equation of a straight line. We know that y-intercept is 9, so b is 9. How about a slope? How about a slope? The line is going downward. Rise over long is 1 over 1. Rise over long is 9 over 9, which is 1. The line is going downward, so it's negative 1. Slope is negative 1. this line is going downward. Slope is rise over long. 9 over 9 is 1. The line is going downward, so slope is -1. Y-intercept is 9. So this equation, this boundary can be rewritten as y equal to -x plus 9. That's the same as 9 minus x. So this boundary, -x plus 9, can be rewritten as 9 minus x. So this is another boundary here. Next, let's try to find critical point first. Let's try to find critical point. For f sub x, we take partial derivative with respect to x. I have 2 minus 2x. For f sub y, I take partial derivative with respect to y. I have 2 minus 2y. Set each of them equal to 0. Solve for x and y. Solve for the first equation for x equal to 1. If I solve for the second equation for y is also 1. So the critical point is 1, 1. One comma 1 is here. It belongs to set D. Next, we try to find critical point on the boundaries. On the boundary s equal to 0. On the boundary s equal to 0, y is between 0 and 9. If I substitute 0 for x, I have f of 0 comma y equal to 2 plus 2y minus y squared. This is a single variable function. Let's call this function g1. Variable is y. If I take derivative from the function, g1 prime of y is 2 minus 2y. If I set equal to 0, y equal to 1. Y equal to 1, 1 is between 0 and 9. So this value is valid. So the critical point when y is 1, s is 0. Critical point is 0, comma 1. On the second boundary, on the boundary y equal to 0, on the boundary y equal to 0, x is between 0 and 9. So I plug in 0 for y. I have f of s comma 0. If I substitute 0 for y, I have 2 plus 2x minus x squared. This is a single variable function. Variable is x. Let's call this function g2 of x. In order to find critical point, I take derivative. g2 prime of x is 2 minus 2x. If I set equal to 0, s equal to 1. 1 is between 0 and 9, so this value is valid. When s is 1, y is 0. When s is 1, y is 0. So the critical point is 1, comma 0. That's the critical point on the boundary y equal to 0. The third boundary. On the boundary y equal to 9 minus x. On the boundary y equal to 9 minus x is between 0 and 9. I plug in 9 minus x for each y. So f of xy can be rewritten as f of x comma 9 minus x. I have 2 plus 2x plus 2 times y. Y is 9 minus x squared minus 9 minus x squared. This is a single variable function. The variable of the function is x. Let's call this function g3 of x. If I simplify the function, I have 2 plus 2x plus 18 minus 2x minus x squared. minus 81 plus 18x plus x squared minus x squared. If I combine like terms, I have negative 2x squared plus 18x. 2 plus 18 is 20. 20 minus 81 is negative 61. Next, I take derivative to the function. I get negative 4x plus 18. Set equal to 0. Set equal to 0. I have x equal to 18 over 4, which is 9 over 2. 9 over 2 is between 0 and 9. So this x is valid. When x is 9 over 2, I can plug in to find y. Y equal to 9 minus 9 over 2, which is also 9 over 2. So the critical point is 9 over 2, comma 9 over 2. And also we must include for absolute maximum, absolute minimum, we must include the endpoint of each boundary. Endpoint of the first boundary is the point 0, 0, 0, 9, and 9, 0. So next, let's test for absolute maximum and absolute minimum. The interior critical point is 1, 1. Critical points on the boundary is 0, 1, 1, 0, and 9 over 2, 9 over 2. And the endpoint of the boundary is 0, 0, 0, 9, 9, 0. Next, we plug in each point into the original function. Using my calculator, I get 4 when I plug in 1, 1. I get 3 when I plug in 1, 0. I get 3 when I plug in 0, 1. I get negative 41 over 2 when I plug in 9 over 2, 9 over 2. I get 2 when I plug in 0, 0. I get negative 61 when I plug in 9, 0. I get negative 61 when I plug in 0, 9. So the largest is absolute maximum. Absolute maximum is 4. The smallest is absolute minimum. Absolute minimum is negative 61.